don't feel obliged to do the whole thing. That's the only topic. Okay? The other topics seem pretty perfectly manageable, the integral functions, etc. Okay, so let's review where we were. We had studied continuous characters from the del group of K, which were trivial on K star, with values in C star. Those were called the Hecke characters. Continuous homomorphism. We saw a number of things about these homomorphisms. First thing was that every such homomorphism, when you just thought of it on the dels, you could restrict it to a local completion and call that chi v is a character of kv star for all v. And we know chi if we know all the chi v, so we could write chi as the product of the chi v. But you can't take arbitrary characters of kv star and make a character of the dels, because, first of all, how do you make this for you? Okay. How do you make an infinite product? So we found that these local characters, when we looked at them at finite primes, almost all of them were unramified. And conversely, if we had characters that were, oh, this is useless too, sorry. Well, that's a little better. I don't know who breaks these before they get here. Okay, so it's a character kv star, and for v a finite prime, chi v is trivial on av star for almost all primes p. So you can't take arbitrary, you don't get arbitrary local characters, but because it's a character in E dels, it has to be trivial on the units for almost all primes p, and if you have a collection of such characters, you can take a product of them and evaluate it on E dels. It's not clear that it's trivial on K star. But, so this has this form. All right, and even if it wasn't trivial on AV, we found that chi v, if not, chi v is trivial on some subgroup of the form 1 plus pi v to the fv times AV. So we had a filtration of the units, and if we got a continuous, if we restrict it to the units, we got a continuous character of this compact group with values in C star, which has no compact subgroups. It has only, it becomes a character of finite order, and so it's trivial on something like this. And so we assign to chi an ideal, its conductor, I'll call it f of chi, which is the product over the finite number of p, where chi v is not unramified, and we took the first power where it was trivial, pv to the f. So for example, if you had a character which was trivial on all unit groups, its conductor would be the ideal 1. Okay, so for a Hecke character, we have its local components. Almost all at finite primes are trivial on the units. The ones that aren't trivial on the units are trivial on some subgroup of this type. That allows us to find an ideal of the ring of integers, which is the conductor of the character. And then we saw that to such a Hecke character, we could assign a homomorphism from the ideals prime to f, this conductor, f of chi, to C star, which took an ideal prime to f, say the product of qi to the mi, where these are prime ideals, and it took it to, well, if chi v is trivial on AV star, then you can evaluate it on any uniformizing parameter. That number is well defined and determines the local characters. So the local characters are determined by these complex numbers in almost all places. And we map this to the product of chi qv of pi v to the mi power, q vi or something like that, product over I. So at each one of these primes, that's relatively prime to f, we have an unramified character. We evaluate the Hecke character on a uniformizing parameter. We get a complex number. We take those complex numbers to the mi power and take their product. And we saw that this function on ideals prime to f completely determined the Hecke character, assuming that it was trivial on k star, because we saw that k star, since k star times the restricted product of p not dividing f of k p star is dense in A, and our character is trivial on k star, and this thing determines the character on this restricted product. We saw that this completely determines the Hecke character. And we saw that on principal ideals congruent to 1 mod f, the value of this had to be given by the components of chi at infinity. In particular, special case. If chi v is equal to 1 for all v dividing infinity, then this function phi is trivial on the principal ideals which are congruent to 1 mod f. So is a character of the finite abelian group IF mod PF. We saw this group was finite. And if you didn't have quite this, but if chi had finite order at infinity, so more generally, if chi v is equal to 1 for all complex v, places v, and if chi v is equal to 1 or the sign for all real places v, so those are characters of finite order of this product at infinity. So, right, I mean, if you take the product of v dividing infinity of kv star, so that's a product of reals and complex numbers. There are no characters of finite order of the multiplicative group of complex numbers, but the characters of the multiplicative group of real numbers, you could either have the trivial character or the sign. So if I didn't assume it was trivial, but assumed it was either trivial or the sign, then chi is trivial on not PF, but PF plus. So you need to have ideals which are principal. Alpha has to be congruent to 1 mod f, and alpha has to be greater than 0. This alpha congruent to 1 mod f means these local characters are trivial because they're trivial on this subgroup, and it being positive generator means the real character, even if its sign is trivial. So you get trivial on a subgroup of PF of the things with a positive generator, and that's again a finite group. So we find, so the moral is, the Hecke characters of A star mod K star of finite order on the product of v dividing infinity kv star are in bijection with characters of IF mod PF plus for ideals F of a ring of integers. So every Hecke character of finite order on this, and conductor, let's say in conductor F. So this is the Tate way of viewing a Hecke character, and this was Hecke's way of viewing a Hecke character. A finite order character, and this has to be a finite order because this is a finite abelian group. We already saw that. We don't really know what it is, but it's a finite abelian group. So if I have a character of this, and I go backwards using the denseness of this, and I use the character to define it here. I say it's trivial here. I extend by continuity. That gives me a character of A star mod K star. Okay? Now, we're going to see what's so wonderful about characters of IF mod PF plus. Namely, we're going to interpret now this finite abelian group as a Galois group using the results that aren't proved in class field theory. Now, I'm not going to prove any of these results. This is a course in itself to do class field theory. But it's a beautiful thing. The results are easy to state. They're hard to prove. And the proofs give almost no illumination as to why they're true. And I'll show you what the huge gap in our knowledge is. But if you want to see the proofs, I recommend that you take Christian Popescu's course where he's going to do local and global class field theory, and he'll give you the proofs. You tell me after that if you know anything more about it. Okay? Okay, so recall, for example, if suppose their example, if K is complex, namely no real places, so you don't have to worry about this PF plus business, and F is equal to 1, so the character is unramified everywhere, then the chi of trivial on product of AB star b divided by infinity are exactly the characters phi of I mod P, which is the ideal class group. So in particular, if you have a character of the ideal class group, that gives you a Hecke character, trivial on the complex places, and with conductor 1. Okay. Now we go back and we're going to do a little Galois theory, starting with our field K. So, Galois extensions of K. Our number field K, because we have a Hecke character of K, etc. So let's start with just a finite extension. Everything is separable because we're in characteristic 0. So we won't assume yet it's Galois. We'll see what happens when it's Galois. And we're now going to discuss what happens to prime ideals of K in this extension. So here, of course, we have our ring of integers A, and here we have a ring of integers AK. And in our ring of integers, we might have a maximal ideal that we call P. I mean, that gives us our valuations of K. Okay, so then associated to this prime ideal, we do what we did thinking of K as an extension of Q. We got these ideals of characteristic P by factoring the prime P in A. So we take the ideal capital P times AK. That's an ideal in AK, which contains P times AK. So it's an ideal, and this quotient ring is finite, and the maximal ideals containing it are the primes of AK dividing this. And we know that this is a Dedekind domain, so this ideal has a prime factorization. And I'm going to write it the product of Qi to the EI, I equal 1 to G. So there are G primes dividing it. We don't know what they are yet. They're all of residue characteristic P, and they might occur with some multiplicities. Okay, now, if you have a prime that divides this ideal P, then if you map, then when you intersect Qi with A, you get the ideal P, and so you get an injection of the residue field. This is finite of characteristic P. Say it's of order Q. It injects into the residue field of each one of these factors. In other words, think of this as first you map A into this, into A mod K, then you map it to this field, right? So the kernel of that has got to be a maximal ideal of A, and it's only, the only possibility is P. So you get a field extension here. Let's call this, so this is also a finite field of characteristic P, so say this has order Q to the F. this will be an extension of degree f, and I'll call it fi because it depends on which prime factor I choose for p. So associated to each factor of this ideal p, I get the exponent of it in the factorization, and I get the degree of this residue extension. Okay, and it's not hard to prove that if you sum from I equal 1 to g of ei times fi, that's equal to the degree of this extension. Because, well, that if you calculate this index, so this index here is q to the fi, and then you have to work your way down to here, and then the index here is p. Okay, I'll leave that alone. Okay, so that's the general theory of factoring primes in an extension. But now we assume that the extension is Galois with group G. So it's a separable extension, and the automorphisms of k that fix little k have the same order as the degree. Well, then some wonderful things start to happen. Okay. So the first thing that happens, and again, I'm just going to assert this without proof, and you can find the proofs in all the books, is the first thing is that G acts transitively on the QI that divide P. And that implies that all the exponents are the same, and all the residual degrees are the same. And in particular, we get the formula that G times E times F is equal to the degree, which is the order of the group. Okay, so that's the first important statement. Again, I think this is all due to Frobenius, but don't know the exact references. So let's let GQ be the stabilizer of one factor. Since it acts transitively, it has index G, because they're G different factors, right? And so the order of this subgroup is E times F. This is sometimes called the decomposition group of Q. All right, well, if it stabilizes Q, then it acts on the residue field. So GQ acts on AK mod Q. And it fixes this field because it fixes everything in A. It's part of the Galois group, right? And fixes image of A. So we get a homomorphism from GQ to the Galois group of this field extension. Let me come up with some names here. Let's call this FP. Let's call this F. I mean, I fixed the Q. So it acts on the Galois group of FQ over FP. There's a homomorphism from GQ to the Galois group. And the kernel of that homomorphism, which is called the inertia group at Q, are the elements that stabilize Q and act trivially on the residue field, by definition. Right? So we have, certainly that's a normal subgroup of G of Q. And the second big theorem beyond the first theorem is the transitivity. The second main theorem proved by Frobenius is that this homomorphism is surjective. So that you get every automorphism in the Galois group of the residue field from an element in the decomposition group. Not uniquely, it's only well defined up to the inertia group, but it's at least surjective homomorphism. And in particular, this group we know has order F. And in particular, this group has order E, because GQ has order E times F. So for every factor, we get a subgroup stabilizing it, and the subgroup of that acts trivially on the residue field has order E, and then the quotient is the Galois group of the residue field. Okay, now since E, didn't say that. I should have come back here. Okay. Just like in the extension from Q to K, there are only finitely many primes that ramify, the primes that divide the discriminant. There's an ideal of little k called the relative discriminant of capital K over little k, and there are only finitely many ideals that have EI greater than 1, and those are the ideals that divide the discriminant of E over K. So let's say that. Before we get to Galois theory, there exists an ideal E of K over K in the ring of integers A with the property that P has a factor with E greater than 1 if and only if P divides the K over K. In particular, only finitely many primes of little k have a factor that appears with multiplicity greater than 1. If you think of this as, I mean, the way we saw that for K over Q was we wrote this as Q of alpha, where this satisfied some polynomial f of x, and the primes where there was a multiple factor were the primes where this had multiple roots mod p. And since it doesn't have multiple roots in characteristic 0, there are only finitely many prime p's and divided discriminant. The same thing happens here. Okay, so for almost all primes p, this group is trivial. So let's write that down. So this is 1, this is 2, then it's surge x onto here, and 3 for almost all p, namely those not dividing this relative discriminant, the EP or EQ is equal to 1 for all q. So the decomposition group at Q is isomorphic to the Galois group of the residue field. Okay, what is the Galois? Now comes the big idea. What is the Galois group of an extension of a finite field? Well, it's a cyclic group, but even stronger than that, it's canonically a cyclic group. And the canonical generator of this cyclic group, so this is a group like Z mod F. We're now doing, just one P and one Q, right? It's a cyclic group of order F, but it's stronger than that. It has a canonical generator, which I'll call FR of Q. And the Frobenius is the element that takes any element in this finite field and raises it to the qth power. That fixes all the elements in this finite field. And it has the property that when you raise it to the f power, it fixes everything up here. So Frobenius Q of alpha is equal to alpha to the q, where q is the order of the residue field here. Okay, so this group is canonically Z mod F times the Frobenius at Q. I'll write it like that. And how do we say which is the element is the Frobenius at Q? So that gives us, you see, and that's the remarkable thing that Frobenius noticed. It says that for all these primes that are unramified, and that's almost all of them, once we pick a factor, we get an element in the Galois group, GQ, which is a subgroup of the full Galois group. So for P not dividing P over K, and Q dividing P in AK, we get an element FR of Q in GQ, which is a subgroup of the Galois group of capital K over K. Namely, it's characterized by Frobenius of Q on any algebraic integer is congruent to alpha to the q mod q. So that says that it's action for alpha in A. It's action on anything in here, if you look at it, mod q is just raising to the q's power, because that's what Frobenius does on the finite field extension. And that'll help us identify it in some simple cases. Okay, so this theorem of permuting the primes transitively, that it maps surjectively to the Galois group of the residue field, and that we know what the Galois group of the residue field is, allows us to construct, for the primes dividing unramified primes, elements in the Galois group. All right, that's the third thing. 4, what happens if q prime is equal to g of q for g and g? Remember that the primes dividing p are permuted transitively. How does this element, well, then we find that the stabilizer of q prime is the conjugate of the stabilizer. I think I did that right. Let's see. If I take, right? Let's see that. So start with an element in q prime. G inverse takes that to something in the prime q. This stabilizes the element in the prime q. This takes it back to the prime q prime. So this thing stabilizes the prime q prime. Okay? Moreover, and this also Frobenius proof, the Frobenius at q prime, the canonical generator of this group, when p is unramified. So this is true in general, that the decomposition groups are conjugate. But when p is unramified, the canonical generator of this group is the conjugate of the canonical generator. You might expect that's true. G inverse. And you have to use this characterization. Okay? So, corollary of that is for every p which is unramified in k over k, we get a conjugacy class of Frobenius of any prime q dividing it in G. We don't get an element, but we get a conjugacy class, because all of these different elements that we've defined are in the same conjugacy class. That's a consequence of the transitivity. And then, miracle 5, if G is abelian, so if the Galois group turns out to be abelian, then a conjugacy class is equal to an element. Namely, the group doesn't move things around. And so we get an element, so then all FRQ prime is equal to FRQ for all the different factors of P, and we just call that the Frobenius at element at P. So get an element called the Frobenius at P in G. Here we get a conjugacy class, which I could call the Frobenius at P, because it only depends on the prime P, not on the factor. But in the abelian case, since conjugacy classes are just an element, you get an actual element in the group. Okay, so that's an amazing thing that Frobenius noticed. And let me just show you an example to show you how powerful this is. So let's do this example, because this is the key example that motivated everybody. Let's take the nth roots, well, let's take the f roots of unity over q. And here the Galois group we happen to know is Z mod f star. That's a Galois extension. And the way you make an isomorphism of the Galois group here with Z mod f star is you say to each A, which is relatively prime to F, you assign the element sigma A, which takes a root of unity to its 8th power. An automorphism of this field has to take a root of unity to some other F root of unity. And if A is relatively prime to F, these two things have exactly the same order. So there is an order, and you have to prove that that map is right. I mean, in general, of course, G is just a subgroup of Z mod F star. If I took this to be the complex numbers and this to be the complex numbers, I wouldn't get Z mod F star. If I took this to be the real numbers, I took this. But so in general, there's a map from the Galois group to Z mod F star, which takes an element in the Galois group and sees what it does to sigma, and that gives you a class mod F, and that's that's an inclusion in the Galois group, and the miracle is for the rational numbers, the cyclotomic polynomials are reducible and it's surjective. Okay? Okay, so in this case, P is unramified if and only if P does not divide F. F is the discriminant of this is made up of primes dividing F to various powers. In fact, if F is a prime, if F is a prime L, we saw that the discriminant of capital K over Q was L to the L minus 2. Or was a minus 1 here? L minus 1 over 2 times L to the L minus 2. In any case, there's a formula for it which only involves powers of primes dividing F. So if P does not divide F, we're good. What is the Frobenius element? I claim, this seems so stupid, but here it is. The Frobenius of P is equal to the class of P in Z mod F star. I mean, I've identified the Galois group of this. The Frobenius of P is some class in here because it's an abelian extension. So it's the class of P. Why? Well, we have to see what Frobenius of P does to zeta. Okay. So the Frobenius of P of zeta is congruent to zeta to the P modulo from prime capital P dividing little p. Right? Because Frobenius is defined by this thing, and the order of the residue field is of the base prime is little p, so it's right. Okay? But that forces it to be equal to zeta to the p. But this is equal to some power of zeta, and if zeta to the a is congruent to zeta to the p mod capital P, then a is congruent to p in Z mod F star. Namely, these powers of zeta are equal. In other words, zeta to the a is equal to zeta to the p. And that's because these are two roots of the cyclotomic polynomial, and p doesn't divide the discriminant of the cyclotomic polynomial, so roots that are different in characteristic 0 will remain different mod p. So this is saying these two roots are equal mod p, and therefore they have to be equal in characteristic 0. And therefore, therefore, this thing implies that, in fact, Frobenius P corresponds to the class of P. Okay, now what does Dirichlet's density theorem say? Dirichlet's density theorem now says that for any class in this group, there are infinitely many primes P which are congruent to A modulo F. Dirichlet density says there are infinitely many primes with Frobenius of P equal to congruent to A mod F for any class. So, in fact, the density we saw is 1 over the number of elements in the group. All the primes distribute them equally in the different classes. Okay, so Chebytarov proved the generalization of that to extensions of number fields. His density theorem, and it applies in this case, 6, Chebytarov. And this is a critical result in the proof of global class field theory, which we're going to get to a statement of in a minute. Chebyshev density, there for each conjugacy class C in G, there are infinitely many primes P of K, where with the class of Frobenius P in C. And moreover, the density is exactly what you'd expect, is equal to the order of C divided by the order of G. So primes distribute themselves equally in conjugacy classes. So in the abelian case, they distribute themselves equally in terms of elements, and in particular, every element in this Galois group is a Frobenius at P for some primes, for an infinite number of primes P. Okay. Okay. Now we're ready for Artin reciprocity, which is the big statement. 5, 6, 7. Artin reciprocity. Let F be this relative discriminant of K over K, for example. And define a homomorphism from the ideals prime to F to this abelian Galois group. So again, we're now in the abelian case, where we have Frobenius elements. By saying, to every prime which is relatively prime to F, we take it to the Frobenius at P. Okay, that makes sense. And then you extend multiplicatively over primes. So any ideal prime to F has got a prime factorization, and you just extend this to a homomorphism. So since, by the density theorem, this is a surjective map, because there are infinitely many things that hit each element. Okay? And Artin reciprocity concerns its kernel. Okay? And the statement is, let's call this map R for reciprocity. The kernel of R contains PF plus. Namely, when you extend this to all ideals prime to F, and you restrict to an ideal which is sufficiently congruent to 1 mod F, and is positive generator, and is principal, then it is in the kernel of that map. The product of the corresponding Frobeniuses is trivial. Look at it over here. If the Frobenius of P is P, and I take an ideal N, which is the product of Pi to the AI or something like that, where N, the generator of N, is positive and is congruent to 1 mod F, then what does this product of Pi to the AI come to? It comes to this product in Z mod F star, which is 1. So it's in the kernel. Okay. And consequently, every abelian Galois group over K can be written as a quotient of these general class. This is called a generalized class group. Generalized. Because in the case of F equal 1, it is the ideal class group. So every abelian Galois group is canonically the quotient of a class group of some conductor, and the conductor has to do with the primes that ramify in the abelian extension. So it's a special case. Take a look at the case F equal 1. That would be a case where all the primes are unramified. You don't have such extensions of Q, but there are such extensions, for example, of imaginary quadratic fields. If we had an abelian extension G, where all P of A are unramified, in K, which means where P is equal to 1, then G is a quotient of I mod P plus, the strict class group. And so that says that it's only a finite abelian extension which is unramified everywhere because it's bounded by this. And that's not true for non-abelian extensions. You can make infinite non-abelian extensions of even real quadratic fields that are unramified everywhere, but for finite abelian extensions, it's abelian. It's a quotient of that. So that's the first statement of global class field theory, that this homomorphism that's defined by taking primes to their Frobenius elements identifies the Galois group with a quotient of a general class group. And the second statement, which is the part that's not very well understood at all, is called the existence theorem. And the existence theorem says maybe there are no abelian extensions. I mean, if every abelian extension were trivial, then its Galois group would certainly be a quotient of the ideal class group. No problem. Okay? The existence theorem says for every conductor, ideal F in A, there is a canonical abelian extension K, which I'll call little kf of K, with Galois group IF mod PF plus. And namely, this whole quotient appears as the Galois group of an abelian extension. So this we saw. So for example, this is the field Q of F, because we saw that for the rational numbers, IF mod PF plus was equal to this group. So the class field for the ideal F of the rational numbers is given by the F roots of unity. That case is perfectly satisfactory. One knows everything. And one uses that case, by the way, in the construction of this. This is called, this abelian extension is called the class field of conductor F. The reason it's called a class field is that its Galois group is a generalized ideal class group. Okay? And so it gives a construction of abelian extensions coming from the structure of these groups. The problem is that in most cases, one doesn't know anything about this group, and because we don't know anything about this group, we don't know how to construct this field. It's a general proof of existence without actually seeing how to get there, what we adjoin to K to get the class field. The only case where we really understand these generalized class groups is for the rational numbers, where the class fields are cyclotomic fields, there. And in the case where K is Q squared or minus D, or D is less than 0, imaginary quadratic fields, then we saw that IF mod PF maps to the ideal class group, which is something we're supposed to know, and the kernel is AK mod F star modulo the image of A star. And in this weird case, one actually knows what A star does inside of this group because it's a finite group. It's generally just plus or minus 1. And so we have an idea what this group is. I mean, this makes sense. This is true for general fields, but we just have no idea where the units are in this finite group. They might kill the entire finite group. So if I said to you, what's the size of the class group for a real quadratic field? Forget the Galois extension, but what is this group? You'd have to go compute the fundamental unit, and then you'd have to go see where it landed mod F, which is highly mysterious. But for imaginary quadratic fields, this is very nice. I mean, this basically, you know, is just plus or minus 1, and so one has an idea of the size of this. and you construct the class field in two different steps. You start with the imaginary quadratic field, and you first construct the class field for f equal 1. So that's the maximal abelian unramified extension where the Galois group is the ideal class group. And then you construct an extension of that where the Galois group here is AK mod F star modulo A star. And this two-step construction is usually called the theory of complex multiplication. Well, I may even say a word about this when we get to the end of the course, which is coming up next week, because Hecke characters that are not of finite order, this is only characters of finite order on the infinite part, give characters of this finite group. But if they're not of finite order, we had some examples of that for imaginary quadratic fields, then they sometimes correspond to elliptic curves with complex multiplication. And elliptic curves with complex multiplication came in the 19th century to construct the class fields of imaginary quadratic fields. And for example, to actually define the elliptic curves with complex multiplication by the ring of integers A, you had to get to the Hilbert class field, and then you would join the F torsion points on them to get to the F ray class field, just like these F roots of unity are like the F torsion points in the multiplicative group. The multiplicative group happens to be defined over Q. But when you try to do elliptic curves with complex multiplication, you first have to get to the Hilbert class field, then you could join their F torsion to get to here. Okay, totally beautiful theory, and that was Kroneker's dream of his youth. And those are the only two cases where we know how to construct the class field. And in particular, if anyone can construct the class fields for real quadratic fields, that would be a huge breakthrough. But as I say, you first have to tell me what this group is first. Okay. Now, what does this all have to do with Hecke characters and things of that nature? Getting a little carried away here. Okay. Well, we know that the characters of this group correspond to Edel class characters. So if I define the L function of a character of this group, let's call this character psi or something, L of psi s to be the product over the primes of k that don't divide f of 1 minus psi of p, norm of p to the minus s inverse. So that infinite product converges when the real part of s happens to be greater than 1. And this is a function now on this group, but I get such a character if I have a character of the abelian Galois group. So if I have any character of this abelian Galois group, C star, that gives me a character of IF mod PF plus, and then from that I can make an L function which satisfies a functional equation. Right? So let's state that. So since we know that characters of these class groups behave well, let's see if we have what happens when we have a character of a Galois group. So we have an extension where the group is G, and we take a homomorphism from G to C star. So this is a finite abelian group. And we define the following infinite product following Artin, L of chi s. Well, we take the product of the primes that don't divide the relative discriminant, so they're unramified. And for each such a prime, we have a Frobenius element in the Galois group, and I can take chi of the Frobenius element and get a complex number. And I take 1 minus chi of the Frobenius at p times the norm of p to the minus s inverse. So that defines a complex function in the half plane real s greater than 1. And it's exactly the same as this function, because remember, in this isomorphism between IF mod, or the surjection from IF mod PF plus to G, we took the prime P, which is what we put in here, to the Frobenius element. Okay. And then it follows from Hecke's functional equation that if we do the following, so if we define lambda chi s by putting in the factors at infinity, which means you take the product over the complex V of little k, gamma C of S, and then you take the product over the real V, which split in K. So if you have a real place here, it either becomes complex or it splits into two real places. And if it splits, you put gamma R. Sorry, that's not quite right. Right. Yeah, that's good. The real V, sorry, that does better. Real V with chi of Frobenius at V equal to +1 of gamma R of S. What does that mean? So if you have just like for a finite prime, you get an element in the group. Also for real places, if they split in K, you get no element in the Galois group. But if they remain complex, then you get an element that generates the Galois group of C over R. And in an abelian case, that really is an element of the Galois group. And we call that the complex conjugation. So when you calculate the character on that, it's either +1 or -1, because it's an element of order 2 generating the Galois group of C over R. And you take the product of gamma R S +1 for the chi of the real places, well, -1. So this is, you take that and you multiply it by L chi S. So this now has an Euler factor in every prime of K. The factors at primes dividing the discriminant is 1. The factors at complex places are this gamma function. The factors at the real places that split are these gamma functions. The factors at the real places are these gamma functions. That this satisfies the functional equation. And the functional equation is the following. It's exactly Hecke's functional equation, because all we're doing is putting in the factors at infinity that appear in Tate's thesis to get the functional equation for this. Okay, and the functional equation is that lambda chi S is equal to the absolute value of the discriminant of K times the norm of the conductor of chi. So that's, we've already defined the conductor of a Hecke character. That's some ideal of K. You norm it down to Q, you get a positive number to the 1/2 minus S power times W of chi times lambda of chi bar at 1 minus S. Because that's the functional equation where this is some constant of absolute value 1, which was a ratio of Gauss sums when we did it for the Dirichlet-Leal functions. And this is exactly the functional equation we proved for Dirichlet-Leal functions. But now we can think of them as functions on this abelian Galois group. But instead of evaluating it on the ideal P, we evaluate it on the class of Frobenius, which is the same thing. So this is a function on the Galois group. Good? So for every abelian extension and character of its Galois group, we get an L function, generalizing Dirichlet-Leal functions. We can complete it using the methods of Hecke and Tate and get an analytic continuation of functional equation. Okay. Now, Artin didn't stop there. And that's what's leading into such cool mathematics nowadays. Let's see if I can find my missing piece of chalk. Oh, it must be under all this. Okay. Artin said, well, what happens if I have a non-abelian Galois extension? Okay, let's take out this. I don't have class field theory anymore. I can't avoid. And if I have a non-abelian group, I don't want to just take one-dimensional representations. The generalization of a character would be a homomorphism from the group to the general linear group of some vector space over the complex numbers. Suppose I had that. Can I make an L function that generalizes this? And he did. And he conjectured that it had the same properties as the L functions of characters of abelian extensions. So I'll just end by defining the Artin L function, because we have everything we need, of a complex representation V of our Galois group. generalize this term? Okay, well, again, to V, Artin assigned an ideal called the conductor of V. It had to do with which primes. We'll see what it has to do with in a second. And the L function of Vs, at least the finite part, was an infinite product over primes, P of K. P doesn't divide the conductor of the representation, which is a generalization of the conductor of this character. And what does he put in here? Well, now the Frobenius at P is only a conjugacy class in here. And if you have a conjugacy class, you don't get a matrix, right? But we understand conjugacy in GLV. It's an element of finite order, right? Because it's a finite Galois group, so it goes to something of finite order. So it's a semi-simple conjugacy class in the general linear group. And an invariant of a conjugacy class is the characteristic polynomial, right? If I have a linear operator T, I can take it to the characteristic polynomial of T, x, which is the determinant of x times the identity minus T for any minus A for any matrix representing T. And if T is conjugate to another operator S, they have the same characteristic polynomial. So that was Artin's brilliant idea, to take this conjugacy class and turn it into a characteristic polynomial. And he does that. He takes the determinant, well, he does it this way, but it's the same as the characteristic polynomial, 1 minus the Frobenius at P, which is just a conjugacy class, times the norm of P and a minus S inverse. So this is a polynomial of degree equal to the dimension of V in Q to the minus S, right, in this norm of P to the minus S. And the coefficients of that polynomial depend on the conjugacy class of Frobenius. They have to do with the eigenvalues of Frobenius, right? But that only needs the conjugacy class. And in general, on V. And instead, Artin went even further, and he realized that he could avoid just taking this product of primes that didn't divide the conductor. He could take the product over all primes, but you couldn't evaluate Frobenius on V because it wasn't well defined. But it was well defined if you took the invariance of inertia on V. Because remember, we had this inertial subgroup that was we had the sequence 1 goes to IP, goes to GP, goes to the subgroup generated by the Frobenius. Well, at least for every prime dividing it. If you take the invariance of inertia on the vector space, then the group GP modulo inertia acts on the vector space, so Frobenius acts. So this is a polynomial of the degree, the dimension of V fixed by IP. And for almost all primes, IP is the trivial group, so this has the dimension of V. So this would be a polynomial of degree n, where V had dimension n. But for the primes that ramify, it'll be a smaller degree. Now notice, you see, for a representation of degree 1, if you take the invariance of inertia, right, it's going to be the 0-dimensional representation, so you don't get anything. So then it's just these primes. But for higher dimensional representations, Artin realized you got smaller and smaller degrees when you took this Artin function. And Artin conjectured that just like the abelian case, this should have a holomorphic continuation to the plane and should satisfy functional equation, the whole thing. And Brouwer was able to prove much of Artin's conjecture, but the key part, the holomorphic continuation, is still unknown. That's Artin's conjecture. And I'll start with that on Thursday. Okay? This is enough for a day. All of class field theory. And then, as I say, Artin not only did this reciprocity law of class field theory, identifying these abelian Galois groups canonically with these class groups, but then had the vision to say what to ask for in the non-abelian case. And it's going to higher dimensional representations of the Galois group. Good? No, notice, think of us also, anytime you have a conjugacy class in a group, like this abstract Galois group, and you have a homomorphism from that group to another group, like GLV, or the symmetric group, where you have an understanding of the conjugacy classes. like in the general linear group, you know, that's not determined by the characteristic polynomial, but that's an invariant. In the symmetric group, they're determined by the cycle structure. So if you have a homomorphism from your Galois group to the symmetric group, for example, if your extension K is given by first taking an extension of degree n, and then taking the splitting field, right, K prime, then the Galois group permutes the roots of this polynomial, correct? So that gives a homomorphism from the Galois group to the symmetric group on n letters. It's a splitting field of an nth degree polynomial. So then you could ask, what is the conjugacy class of Frobenius mapped to here? Namely, what is the cycle structure? And here's an exercise for you to see if you understand Frobenius. The cycle structure of Frobenius in the symmetric group is exactly the factorization of this polynomial mod P. So it's polynomial degree n. It's irreducible, right? But when you factor mod P, it has various factors. So if you had a cubic field, if you had n equal 3 here, and the Galois closure was S3, right? Then you'd say, well, you take this polynomial F3 of x, and you look at it mod P, and if it factors completely, that's when Frobenius is trivial, because its cycle structure is 1, 1, 1. And if it factors as linear times a quadratic, that means the Frobenius has order 2. And if it remains irreducible, that means Frobenius has order 3. We'll do a couple of examples of that. So anytime you define a conjugacy class abstractly and you take it into a group where you understand the conjugacy classes, and really the whole theory of linear algebra that we teach, you know, when we get ready to do multivariable calculus or something, is the theory of conjugacy classes inside of this group, right? The minimal polynomial and all, right? So why not use that? That was hard. Okay, I'll see you Thursday. And the paper, let's say the paper is due. Well, I mean, it'd be great if you could get it to me a week from Thursday, but if you can't get it to me a week from Thursday, the week after that as well. Okay? I don't want to run too far into the winter season. Okay?
Are you doing the lunch with Ilan?
Yes, okay. So we have a very distinguished visitor, Ila Varma. Many of you went to her talk yesterday on computing invariance of number fields and distribution of invariance and statistics. And we're going to take Ila to lunch, and she's very interested in speaking to graduate students here, particularly graduate students who are interested in number theory. Yeah, but you don't have to go. But if you don't go, I'm going to grade your paper very harshly. Okay? Then I'm going to take a head count. Okay? So, yeah, thanks for reminding me.